Please make sure you have watched parts 1 and 2 of the basic RMC Tools training. This video presents manual tuning of position axes. RMC Tools also offers auto tuning, which is described in other videos. Tuning is necessary in order to control an axis precisely. Before tuning an axis, make sure to complete all the preparatory steps listed in the startup guide, which include verify the actuator moves, configure the feedback parameters, verify the feedback works, set the scale and offset, set the output polarity, set the positive and negative travel limits. The startup guide ships with each RMC motion controller and can be downloaded from Delta's website. To tune an axis, open the Plot Manager and click the Tuning tab to open the Tuning Tools. Each gain and feed-forward value will contribute some voltage to control the system. The sum of all the contributions is the control output voltage that is sent to the actuator. This is done each loop time of the motion controller. The manual tuning process involves repeating these steps: setting a gain, making a move, and viewing the plot of motion. First, set up the lower buttons, which are used to send commands and automatically upload a plot. For position axes, choose Move Absolute commands to two different positions. Make the speed, acceleration, and deceleration identical on both buttons. For systems that behave differently in both directions, such as a hydraulic cylinder or a motor with an asymmetric load, make sure the symmetrical ratioed parameter is set to ratioed. For hydraulic cylinders or a motor in velocity mode, the following order of setting the gains works very well. First, proportional gain, just a little, velocity feed forwards, acceleration feed forward, then the proportional gain again a bit more, then the integral gain, the differential gain, and the output filter. This is the procedure we will follow for tuning the axis. The proportional gain is the most important gain. It gives an amount of control output that is proportional to the position error, which is the difference between the target and actual position. Therefore, the larger the position error, the more the controller will try to get the axis to the target position. For hydraulic cylinders scaled in inches, the default value of 1 is usually a safe starting point. To move, click one of the buttons. A plot of the motion automatically uploads from the controller. If the plot is not long enough to show the entire target profile, you will need to increase the plot duration, which, as you recall, can be done from the Plots tab. We see that the actual position is lagging far behind the target position. This means we need to increase the gain. Now the actual position is following more closely. At this stage, we should increase the proportional gain only enough so that the target and actual positions parallel each other during the move. Now the positions are paralleling each other, so we can go to the next step, which is to set the velocity feed forward. For a hydraulic cylinder or a motor in velocity mode, the actual velocity is roughly proportional to the control output. That means that for any commanded velocity, we can calculate approximately how much control output is needed. This is what the velocity feed forward does. It gives an amount of control output proportional to the target velocity. The feed forwards are very important and are the reason that the actual position can track the target so precisely even when the target is changing quickly. To set the velocity feed forward, make a move, Then click the Adjust Velocity Feed Forward button. One of the velocity feed forwards will automatically be set. Do the same for the other direction. Now both velocity feed forwards are set, and we see that the target and actual positions now come together during the move. The next step is to set the acceleration feed forward. The acceleration feed forward is like the velocity feed forward, except that it is proportional to the target acceleration. It will add extra control output during the beginning of the move so the actual position can keep up, and will subtract control output at the end of the move so the actual position can slow down quickly enough. The acceleration feed forward is usually much smaller than the velocity feed forward. We will start with 0.01 and make a move. The actual position is still lagging, so we will increase it some more. The actual position is still lagging, so we will increase it again. Now the position is tracking very well. The next step is to increase the proportional gain some more. We should see the target and actual come together a bit more. The position is tracking better now. As the position tracks better, it may be difficult to see much improvement. You can look at previous plots on the History tab to compare. Clicking on the Parameters tab shows which gains were used for that plot. Increasing the proportional gain too much will cause oscillation. If that happens, decrease the value significantly. The next step is the integral gain. It may not provide visible improvement at this point, but it is still important, especially for compensating for changing system dynamics such as temperature changes and machine wear. A rule of thumb is to set the integral gain to 3 to 5 times more than the proportional gain. And we see that the motion is still good. The next step is the differential gain. The differential gain is not needed for every system, but is very useful for systems that change velocity quickly and need very fine control. The differential gain gives an amount of control output that is proportional to the velocity error, which is the difference between the target and actual velocity. The differential gain is usually much smaller than the proportional gain. The differential gain can cause chatter, so be careful and start with the low value. There was not much change, so we will increase it some more. As we increase the differential gain, we see that the control output becomes noisy. This is because the actual velocity is not measured directly. It is calculated from the actual position, and that calculation introduces quantization error. This error is multiplied by the differential gain and creates noise that can cause system oscillation and prevent us from increasing the differential gain. To solve this problem, use the output filter. This low-pass filter smooths the result of the proportional and differential gains. When the value is 0, the filter is off. If you need to use the filter, start with the large value, which does minimal filtering. As we decrease the value, it will provide heavier filtering. We see that adding output filter smooths the control output. Decreasing the output filter smooths it even more. Now, since the output filter smoothed much of the noise, we can increase the differential gain some more. This can be repeated as much as needed. Too much filtering will result in oscillation. These are the basics of manually tuning an axis with the RMC motion controller. Tuning requires practice, and difficult systems may require additional techniques.